Right, hello there. This is the first of two videos on electrolysis, and in this one I'm going to look at molten ionic compounds with you. So I'll start off by defining electrolysis for you, then I'll have a look at why certain substances conduct electricity and why others don't. Now, before we study this, it might be a good idea, if you need to refresh your memory of giant ionic structures and simple molecular structures and their properties. Then we'll have a look at two examples: the electrolysis of molten lead bromide and the electrolysis of molten sodium chloride. So electrolysis is the process by which ionic substances are broken down into simpler substances using electricity. Sometimes they're broken down quite simply into their elements, otherwise it's a little bit more complicated than that, and we'll have a look across the two videos at what happens and why. So anything with a simple molecular structure, for example water, does not conduct electricity. To conduct electricity we need charged particles that are able to move. Now molecules don't have a charge, and also their electrons are not free to move throughout the structure. So anything with a simple molecular structure doesn't conduct electricity. Now this only applies to pure water. If you've got something dissolved in it, like sodium chloride, it'll conduct electricity really well. And tap water is also a good conductor of electricity because of the dissolved ions present in it. Now, if we've got something with a giant ionic structure, for example sodium chloride, that will not conduct electricity when it's solid because the ions are all held together in a 3D lattice by strong ionic bonds, and the ions have no freedom of movement. However, if you heat sodium chloride up so that it's molten, then the ions can move and it will conduct electricity. Or you could dissolve it in water, and most ionic compounds will dissolve in water. Then once again, the ions can move and it can conduct electricity. Now, molten ionic compounds, or solutions of ionic compounds, don't just conduct, they're also what we call electrolytes. So that means they can be broken down into simpler substances using electricity. Now you may be familiar with metals which have a giant metallic structure, so a lattice of positive ions and a sea of delocalized electrons that are free to move throughout the structure. Those will conduct electricity when they're solid, but the key to this is they're conductors. They don't change chemically, they don't break down by the passage of the electricity, like a molten ionic compound or a solution of an ionic compound would. Now let's have a think about lead bromide. This is an ionic compound, and we often do this in the lab because for ionic compounds, lead bromide's got a reasonably low melting point. Now, lead has got Pb2 plus ions, and bromide has got Br minus ions. So therefore the formula of lead bromide is PbBr2. Now, you may be shown this in the fume cupboard in your lab, and this will probably be set up with a bulbous part of the circuit. So when solid lead bromide is tipped in, absolutely nothing happens, the bulb doesn't light. Remember, those ions are held in place by strong ionic bonds and they're not free to move. Now, when you heat this up, the ions are free to move once the lead bromide's melted. And at that point, you'll see a few things happening. Number one, if there's a bulb as part of the circuit, it'll light up for sure. And number two, you will see a silvery coloured liquid forming at one of the electrodes, and you'll see a brown gas forming at the other. Now let's have a think about what happens and why. If you look at the little diagram at the bottom, you'll see that the electrode on the left is the positive electrode and the electrode on the right is the negative electrode. Now, we call the positive electrode the anode and we call the negative electrode the cathode. Now let's put the ions into the cell. So let's put some Pb2 plus ions, put a couple of those, and Br minus, put a couple of those as well. Now, of course, these will be randomly all over the place. Now, opposites attract, so the ions move to the oppositely charged electrode. Therefore, lead ions go to the cathode and bromide ions go to the anode. So at the anode, we see brown fumes of bromine gas. And at the cathode, we will see a silvery liquid, which is molten lead. Now we can show what happens at the anode or the cathode by writing what we call a half equation. So if we put bromide ions as Br minus, they become bromine. Now bromine's a diatomic element, so therefore it's got the formula Br2. Now half equations must balance in terms of atoms. So we've got two bromines on the right hand side, so we need to put a 2 in front of Br minus. But also half equations have to balance in terms of charge. Now we do this by adding electrons to one side or the other. Now remember, electrons have got a negative charge, so what we do on this side is we put E minus, that shows an electron, but there are two minuses on the left hand side, so therefore we've got to put 2 electrons on the right hand side. Now that is a half equation for the process that occurs at the anode, where we get brown fumes of bromine gas being produced. Let's move on to the cathode. So Pb2 plus ions are attracted and they become lead, which is Pb. And the silvery coloured liquid, of course, is molten lead. Now, we've got no charge on the right hand side. So on the left hand side, if we add 2 electrons there, we've therefore got 2 pluses and 2 minuses, so therefore 0 charge on the left hand side as well. Now you might be already familiar with the concept of redox, and if you remember the word, or the words, oil rig, so O-I-L-R-I-G, now oxidation is loss of electrons, reduction is gain of electrons, so if we have a look at here, at the anode on the left hand side, bromide ions have lost electrons, because we can see them here. So therefore, bromide ions have been oxidised. Now oxidation always occurs at the anode. You can write it here. If we have a look at the cathode at the right hand side, lead ions have gained electrons, therefore they've been reduced. And reduction always occurs at the cathode. Okay, so that's lead bromide for you. Now occasionally, when you've finished the electrolysis and you've turned the Bunsen burner off and you've let everything solidify again, occasionally the bulb, if you've got one as part of the circuit, stays on. And that's because the molten lead has frozen, it's turned back into solid lead, but it's connected the 2 electrodes together, and that occasionally happens. Let's have a look at sodium chloride. Now, we know the formula of sodium chloride is NaCl. Therefore, in this molten ionic compound, we've got sodium ions and we've got chloride ions. Now remember, as soon as it's molten, the ions can move and it'll conduct electricity, and the positive ions are attracted to the negative electrode, which is the cathode, and the negative ions are attracted to the positive electrode, which we call the anode. Now let's have a think about what we're going to see here. Now sodium chloride's got a really high melting point, so the sodium metal produced for sure would be a liquid. So I think again we'd see a silvery liquid. Now the Na plus ions become Na, and they do that by gaining 1 electron each. Now remember, reduction is gain of electrons. This process here is reduction. Now, at the anode, our chloride ions are going to produce chlorine. That for sure will be a gas. Now, you'd have to have a lot of chlorine to see it as a pale green gas. You probably wouldn't see any colour at all, but let's put it down as a pale green gas. Now, thinking about our half equation, well, chloride ions, as we know, are Cl minus, and chlorine is another diatomic molecule, so that's Cl2. So what we need to do firstly, balance the number of atoms on either side, so put a 2 in front of Cl minus, and then we add the 2 electrons onto the right-hand side, so both sides of our half equation have got a 2- charge. And this process, as always at the anode, is oxidation. Okay, so that's electrolysis of molten ionic compounds, hopefully made simple. In the next video, I'm going to cover electrolysis of solutions of ionic compounds with you, which gets a little bit more complicated. Okay, thanks for listening.